So thanks for the introduction. Everyone can hear me, I guess. Okay, great. So we are presenting a project that we did at our company, Idealo, to improve some of our processes. Let's quickly go over the agenda. So I'll be talking for maybe 7 to 8 seconds about my company as to clarify the context that we're working with. Then we'll go over the motivation, like what the problem is and what are we trying to solve and stuff. Then Christopher would be talking about the deep learning models we used and our training infrastructure, followed by image tagging. That's problem 1 that we're trying to solve. I'll be discussing that. And next problem is image aesthetics. That's something Chris will be talking about, and so on. So first of all, about the company itself, we're actually been in business for 18 years. And as you can see, we have about 16 million users. That's a huge amount of traffic. The main business is that of product comparison, but we also have e-commerce and hotel price comparison services as well. So let's skip quickly to the motivation. Now, as I mentioned, Idealo has a hotel price comparison platform as well. So what you see is my attempt at finding some hotels in Berlin to stay. And we have about more than 2 million hotels and about 300 million images to work with. Now, when it comes to images and hotel businesses, several studies have mentioned that images of the hotel basically determine a lot about the customer decision process. So like me, you just don't look at the price or the location. You also look at how beautiful or what kind of images, how the hotel really looks like. So doing optimization around images makes sense for a platform like us because, well, more bookings means more revenue for us. Now let's dig into the problem a little. So I looked for some hotel in Berlin, and I saw these 3 listings. Let's just talk about the first listing, which is this. Now I'm pretty sure your brain works like me, so you're probably also thinking like I'm thinking. Is this really the photo you want to have as the offer? I don't think so. Well, some people maybe. The problem doesn't end here. So I dug more into the gallery of the hotel, and what you see here is the first 13 images that pop up. So the gallery actually has 52 images for this hotel. And if, again, you're looking through 10 hotels, you're not going to look for 50 images for each hotel. So you probably are going to look at 10, 15 images like I'm doing, right? So let's see what further problem occurs. So the image on the left is the first image that you see, and the image on the right is at 19th position in the gallery. Now, we can all agree the image to the left is much uglier than the image to the right. So if you want to put a picture of a bedroom up in the front in your gallery, you might as well ensure that it's aesthetically pleasing. It looks good, right? The problem is continuously getting deeper. So we have receptions. The one that appears up is factor of times uglier than the one on the right, which appears at position 17. So in an ideal world, you would want that beautiful pictures in your gallery should appear earlier in the gallery, right? Not later. Let's see the second part of the problem. Here's our gallery again. Now I want you to spend 3 seconds looking really hard at the gallery and tell me if you see what I see. I'll tell you what I see. What I see is this red boxes. Out of the first 13 images, 9 are bedrooms. So you might think, okay, I have too much information about the bedrooms now. How does the bathroom look like? Really, what does the reception look like? Does it have a pool? Does it have a restaurant and stuff? So again, in an ideal world, I would want that earlier up in the gallery, I should have all different areas of my image of my hotel depicted well. So an idea of like ideal gallery would possibly something like this. In the first bunch of images, I would have a bunch of areas. So you see 3 pictures of bedrooms. At 4th position, you have bathroom and stuff. And you would recognize that most of the images are aesthetically pleasing. They don't look particularly ugly. They look good. So if I were to look through the offer, I would actually want to maybe go through the hotel, make a booking, right? So we broke this problem down into 2 parts. The first problem is we want to identify as to which area of the hotel this image corresponds to. So if I'm presented with an image, my model or machine is able to say, okay, this is a bathroom. The second problem we want to address is how beautiful or ugly the image is. So we will come up with some score about that as well. So this is for the motivation. And now Chris will be talking about, oh, I missed a slide. So we, of course, use deep learning to solve our problems. Now Chris will be describing the models and the trading regime that we use.
Yes, hello everyone. So we also use this great transfer learning approach that probably all of you have heard of. And basically we use pre-trained convolutional neural networks. They are abbreviated with CNN here. And these CNNs that we use here are pre-trained on this large dataset ImageNet, where a lot of competitions were fought on. So these are really well-working CNNs on basically a data set of over 1 million images and they can classify 1,000 different objects. So that's what they're optimized towards, classifying objects. And there are different architectures, for example, MobileNet or VGG16. I'll get to that in a bit more detail later. And the overall idea, if you haven't heard of transfer learning, is that you use this pre-trained CNN and you just replace one of the last layers with a layer that actually maps to your output classes. So the amount of classes you need. For example, for aesthetic ratings, we have scores 1 to 10, so we would map to 10 output nodes. Yes, and once we've replaced these last layers, then we start training those new added layers, and later on in the second stage, all of the layers. So this is just an example architecture. In this case, it's VGG16. I don't know if you've seen a CNN before, but here on the left, for example, you have the input image. Then you have a bunch of green convolutional layer blocks, and in between you always have these max pooling layers, and at the very end you have the fully connected or dense layers, where the output of the last dense layer here is a 1,000-dimensional vector, which corresponds to the 1,000 classes of this ImageNet challenge. So here, for example, we would replace the last 3 dense layers, for example, for our transfer learning approach. So the training regime is that at first we only train the new added dense layers with a high learning rate. And once we kind of have burned in these new added weights, we then start training all the layers. So also the convolutional layers that were pre-trained on ImageNet with a lower learning rate, because then basically we just want to nudge the weights a little bit to get even better results. Yes, and it's quite important to not start to train all weights right from the beginning with a high learning rate, because then usually you juggle around the weights way too much, and it slows down training a lot, or actually sometimes it doesn't even converge then. So this is just an example train loss here that we have, for example, for the aesthetic classifier, and here on the vertical axis you can see our loss objective. In this case it's Earth mover loss. I'll talk about that in a second. And on the horizontal axis you have the number of epochs that we trained, and the solid lines are the training just for the dense layers at the end in the first stage, and the dashed lines are then is the loss for training when we train all weights, including the convolutional weights. And yeah, this sort of light bluish line is the train loss, and the purple line is the validation loss. So you can see here, for example, we train the dense layers for 5 epochs, so up until this stage. And once the weights are burned in, then we start training all the weights, and you can see that the loss goes down quite a bit by just nudging around also the convolutional layers a bit. In terms of loss functions, we basically use 2 different loss functions. The standard loss function is this cross entropy loss that is generally used in classification setups. And for example, our image tagging problem that Tanuj is going to present in a second, that's this typical classification setup where there is a ground truth. So there's one label that is true. So for example, it's either a bedroom or not. So it's there's no either or. Whereas, for example, for aesthetic ratings, it's not that crystal clear. So it might be, for example, a score of 5, or it might be a 6. So it's there's no ground truth in a way for that. So for the tagging part, we can use the cross entropy loss. And here you can see what it looks like. You have here the y-hat are the predictions, basically, that come out of the neural network. And the y on the right, this is the ground truth, this one hot vector. In this case, the second class is the true class. And yeah, then we just build the product of the label and the logarithmic prediction. For the aesthetics rating, as I mentioned, we use the difference loss function Earth mover distance. And basically the underlying idea is that there is no ground truth, and we would like to punish a prediction of, or let's say the true score is 5, then we would like to punish a prediction of 4 less than a prediction of 10. The cross entropy loss, we wouldn't make the distinction. Only if we make the prediction 5, the loss goes down. If we make any other prediction, the loss doesn't go down. With the Earth mover distance, we can make the distinction that, like, yeah, a prediction of 4 is not as bad as a prediction of 10 if the true score is 5. So in order to achieve this, we basically just take the difference of the discrete CDFs of both the predictions here on the left and the labels. And yeah, we just square the difference and sum it up. I should say, actually I didn't mention that in the beginning, it's not that we came up with this whole thing, it's a Google paper that we re-implemented. It's called NIMA, but I'll give the references at the end. Yeah, that's the Earth mover distance. I'm just going to show you real quick also the GPU training flow that we kind of have for our project. So on the left box you have the local setup, and on the right you have the Amazon AWS setup. And so yeah, the top layer will be sort of like the things we need at the beginning to set the whole thing up. Then we have like a train phase and an evaluation phase. And at first we basically write our own Docker files, and we build the Docker images, and then we push them to the container registry on AWS called ECR. We also build a custom AMI where we sort of like put all our data sets on, and we set up NVIDIA Docker so that we can run containers that have access to the GPU. For training, we then use Docker Machine on our local terminal. And we have a train script. And basically the idea is with Docker Machine, we launch an EC2 GPU instance, which takes our custom AMI. And then with our train script, we just launch a training container with NVIDIA Docker. And yeah, it also syncs with S3 to copy existing models and store the train outputs. And yeah, for the evaluation phase, it's a similar story. We launch like a GPU instance with Docker Machine. And we launch an evaluation container then. And we then hook it up, this GPU instance, with a Jupyter notebook most of the times. And then we have like some visualizations to look at how the model performs. That's kind of the setup that we're running. Yeah, Tanuj will continue.
So now I present how we solve the first problem, which is that of tagging. So again, the formal definition of the problem is we are given an image, and we want to say that this image comes from this one single area. And for this iteration, we have these bunch of labels: bedroom, bathroom, and the usual labels that you have with restaurants. So the approach I'm going to explain to you is that we iterated through several data sets. So I'm going to talk about the data set and the problems we face with the data set and the corresponding results that we have for that data set. So the first data set we already had is something we just came to call wellness data set. I don't know who coined the term in our company, but whatever. So these are usually a lot of hotels that are not very high quality hotels, so I won't pay 200 euros a night to stay in any of these properties, maybe less. So we use the same training regime like Chris mentioned. And just a little bit about the data set itself. So we had about 2,000 samples of each class, which were divided into train, test, and validation. So it's a completely balanced data set that we have. These are the results that we got. I would just want you to pay attention on the top one accuracy, that's 86%. And what you see on the right is a confusion matrix. And the way you read it is, for example, this number 9 here signifies that there were actually 9 bathroom images that our classifier said was reception. So there were like 9 misclassifications for bathroom and reception here. So you want the diagonal to have the maximum amount of value. So this means a bathroom, 177 images of bathroom got classified as bathroom and so on, right? So we actually looked at what the problem was, where the classifier was screwing up. So we saw a lot of misclassifications where a bathroom was predicted as receptions, like I showed you. And what we saw was, okay, whenever it saw like these rectangular panels and the tubs, our classifier was just calling this a reception. So this is not the case. This basically says there's some kind of bias that the model has developed. The second problem that we saw was, well, this is an interesting one. So everyone can say this is a bedroom, this is a kitchen. The classifier also says this is a bedroom, this is a kitchen. But some poor guy who made up the wellness data set thought both of these were bathroom for some reason. So there's some noise already present in the data set. So we said, OK, now we have two problems, a bias and a noise problem. Let's see what we can do about them. So for bias, the usual way is to throw more data at the model. So we said, OK, we'll first do some artificial augmentation, where we'll do some flipping, cropping, et cetera, to generate some artificial samples. The second thing we'll do is maybe we need more data from external sources, so sources like Google Images. We ran the same thing again, and we bumped up the accuracy a little bit. So that's actually a little less than 88%, just like rounded up. So we're not doing too well, actually. So we said, OK, bias didn't fix a lot of stuff. Let's see what cleaning can do. So the cleaning was basically, the way we did this was, we basically went to every image manually. It was a very painful manual process. And if an image that was actually a bathroom was labeled by some guy as, I don't know, a restaurant, we deleted that image. So we got rid of all the noise that we found in the ground truths. And we bumped up our model performance considerably if you consider that the first time we had 86% accuracy. That's about 5% gain, utilizing low-hanging fruits like augmentation and cleaning. And what you basically see here is that a lot of confusion has gone. So bathroom versus reception problem of bias, it's almost gone. We also had some problems with exterior and pool. So exterior is how the hotel looks from the outside versus pool. That's also gone. We also have a class called foyer. And this still is a problem. But this is also a human problem. For example, what would you call this? Is that a reception or is that a foyer? Who says foyer? Nobody? OK, a couple of people. Reception, everybody else. Anyhow, I was not that sure, which is why I put the image here. So we are at the point where the network seems to mimic a human confusion, which is acceptable for now. So the key learning till now is your model can only be as good as the data. You gotta clean, you have to augment. And foyer for us has been a hard category to predict. The next section is about understanding model decisions. So neural networks are usually accused of not being very interpretable, right? So I throw an image, you have some output, and you don't know why the network made the decision. So we explored a technique called CAM. This was developed by folks at MIT. And what it does is it helps attributing the image area. So what I mean by that is what you see in the example is a classifier for classifying a dog breed. You see the original image here. It has a dog here, but it also has like a human sitting in a car, and the background is a bunch of trees. So a good network would actually try to just use this part, the dog part of the image, to come to a decision, right? And the way this is done is, so you have this last convolution layer and a bunch of filters here, right? And you can see the color scheme as blue, red, and green. Now each of these filters in this layer activate different parts of the image differently. If you just look at the blue one, the blue filter activates highly on the face of human. These red areas of high activation. The red filter activates highly on what seems to be the tail and the face of the dog. The green one activates highest on the face of the dog here, if you see. So if your network has been trained well enough, you would say that the weights corresponding to the red filter and the green filter would be much higher than the weights that correspond to the blue filter. And what are these weights? These basically are the weights that are taken from the global average pooling. So the global average pooling takes like an average. The blue neuron takes the average of the blue filter, the red, and so on. And then you weigh each of these average values and generate a prediction there. So here you can see generate a so-called class activation map. And you can clearly see that the network actually used the body of the dog to make a decision, which is a good thing. So we used the same technique to diagnose our problems. So we looked at some misclassifications here. So we saw a lot of swimming pools getting misclassified as bathrooms. On the left, you see the original image. On the right, you see the heat map or the class activation map for this. So what you see is that on these rails, network basically lay a lot of importance to these rails to arrive at a decision. We looked at another example. Again, it's a pool, but these rails or these metallic pipes are used to call this a bathroom, which is happening quite a few times. Again, the rails of the swimming pool are being used as bathroom. This is a continuing pattern. So we said, okay, let's have a look at the correct classifications on bathroom itself, right? So we said, we picked up some images of the bathroom. And again, you can see a lot of times the tap or the long metallic pipe is being used by the model to call a bathroom a bathroom. This happens all the time. Again, the tap, the metal pipe. Again, the tap and the metal pipe. So now it makes a little bit sense that our network is confused when it sees long pipes and tends to call things as bathroom instead of pools. So we have more learnings here. Attribution techniques like CAM, they lend a lot of interpretability to the model. And it can even help our data collection process by saying, okay, we should collect more stuff that goes in the direction of, I don't know, swimming pools with a lot of railings. So we can make a lot of insights with CAM. Next steps for tagging is we want to explore and add more data, for which we are exploring options like mechanical turking. And of course, the natural extension would be to go with other classes like fitness studios. So that's about it for tagging. Now, Chris talks about the aesthetics part.
Yes. For aesthetics, the goal was to take an image and actually predict a score from 1 to 10, and actually a discrete score, so classes 1 to 10, as to how aesthetic the image is. I know it's a very abstract thing. It's supposed to be abstract, but yeah, that was kind of the goal, and it's sort of like we want it in a hotel domain, so it's supposed to be aesthetics for hotel images. So keep that in mind. And we started off by implementing this Google paper called NIMA and used an open source data set called AVA, which basically has 250,000 images. And for each image, we actually have a sort of like a distribution of ratings. So each image is rated by 30 or 40 people. You can see actually in this case it's more people, but you can see kind of like a frequency distribution there of the scores that this image of a bird actually got. And the mean score would be 6.1, and the standard deviation would be 1.3. So this is different from the classical classification setup where you have one label for an image, for example, bird. Here we have basically a distribution of a distribution of labels for this bird, and this allows us to use the earth mover loss instead of cross entropy. So we went through 2 iterations, actually 3 almost by now, but we're going to present the first 2 here. And in the first iteration, we trained on this open AVA data set and this 250,000 images, and it covers all kinds of domains. So animals, people, houses, cars, you name it. It's not hotel specific. And then in the second iteration, we actually fine-tuned the first iteration model on our in-house labeled hotel data. So we trained the model on the AVA data set, and then we predicted on our test set. And here you can see actually the mean scores from our test set, the true labels in blue. So you can see like here the scores are distributed like from scores from 2 to 8 mostly in these blue columns, and then the orange columns are basically our predictions. So you can see that actually our predictions are pretty dense around the scores 4, 5, and 6, and the classifier doesn't discriminate really well. So the range of scores is way too small. It should compared to the true labels, and it's a similar pattern for the standard deviation. Let's look at a few examples. So here we just see different bedrooms from different hotel offers, and the way they are arranged is that the best predicted score is on the top left, and then it's sort of like in descending row order from the predicted score. So the best image has a score of 4.9 there, and the worst score is a score of 4.0. And you can see the range is actually quite small because it's just ranging from 4.9 to 4.0, which we just saw in the histogram as well. But when you just have a first glance at them, even the first iteration model kind of makes sense, right? Because the bedrooms in the top kind of look nicer than the bedrooms at the bottom. This is kind of the takeaway here. So the aesthetic ranking is working quite well. And the same holds for bathrooms. Again, the bathrooms in the top row look nicer than the bathrooms in the bottom row. So we were quite happy there in the first iteration already. If we look at like specific hotel offers now, so again, this is one offer here on our website, for example, and this offer image is this sort of bedroom image, probably not the nicest. Then we took all of the images we have for this hotel, and we put it through our first iteration aesthetic classifier, and you see the predictions here, again, ordered in ascending order, with the top score on the top left and the worst score on the bottom right. And you can see that actually our aesthetic classifier puts this image of flowers on a balcony as the most aesthetic image, which of course is not desirable for us. And also the bathroom in the top row shouldn't really be there. So this is actually a pretty poor result. This here, we basically, actually the classifier did quite a good job. The offer image is not particularly nice, but the best predicted image is quite a nice image. The bathroom is probably still too far in the front, but yeah, not too bad here. And for this instance, yeah, the offer image currently is really not desirable, and also the prediction from the static classifier is also quite poor. This bathroom image shouldn't be there. So yeah, we sat down and said, okay, yeah, we need more sort of domain-specific data. That means from the hotel domain, and we built a simple labeling app because we just wanted to get a feeling first. Okay, how much data do we need, and what kind of impact is it going to have on our classifier? So we built a little app. We just got like 12 people together at Idealo, and we just started labeling ourselves. And then we got like 1,000 hotel images, and again, 1,000 images doesn't sound like much, but for each image we need more than one rating because we need this distribution of ratings. So we have like at least 10 people sort of rating every image. So it's more like 10,000 labels that we had to get here. And then we fine-tuned the aesthetic model on 800 training images and built a test data set on the remaining 200 hotel images. So here you can see the distribution of predictions now, again in orange, on the second iteration model, and it's already a lot better. So it's not as dense around the scores 4, 5, 6. It's more spread out. Similar story for standard deviation, so that looks already quite promising. And now again, the ranking for the bedrooms, it's, again, the first iteration model worked quite well already. The second iteration model is doing a similar good job here to rank these images. Top row looks nicer than the bottom row. Same story for bathrooms, really. So yeah, second iteration model is still working quite well. Now if we look at the offers, we can see in the first iteration we had this balcony with flowers. Now we have like actually a lot nicer image from, it seems like a living room or a dining room. And also the following images are a lot more, let's say, aesthetic and probably appealing to actually explore this hotel than in the first iteration model or the ones that we currently show. And the bathroom is actually quite there at the bottom. So in general, we have a bathroom bias in aesthetics now, which is kind of desirable. So bathrooms are punished quite badly, even if it's a nice bathroom. Similarly, for this offer, the gallery looks a lot nicer now if you rank them with according to aesthetics. So quite happy there. Bathroom is like ranked 12 out of 13, so quite good. And also for this example, before we had this, I forgot what we had. Oh yeah, this ugly looking bathroom. Now it's really a bunch of nice looking bedrooms and generally nice angles and good looking hotel images. So we're quite happy with this here. Just real briefly, we have around 300 million sort of hotel images that we had to predict with aesthetics, and we used our internal sort of OpenShift cluster for this, and we scaled at times up to 100 pods and just sort of like, got those 300 million predictions in around 2 weeks. And yeah, for example, this is a distribution of 100 of a million scores, for example. So you can see already, yeah, the classifier, even in production, he's discriminating quite well. So low and high scores. And again, if you look at some low scores, they're not particularly appealing. Some middle scores, yeah, they look kind of nicer. and some high scores. They're actually quite appealing hotel images, so we're quite happy with the results in production as well. And also, like, in order to get a bit of intuition as to how the static classifier, what's actually going on, and yeah, we started visualizing the convolutional filters. And as you saw in the beginning, like this one graph where the loss actually decreases quite a bit once you start training the convolutional layer weights, we wanted to understand which weights or which convolutional filters get actually sort of amended when you train them for aesthetics. And here in the top row, you can see the 6 filters out of layer 23 from MobileNet original. So that's the one trained on ImageNet. And you can see those filters on our MobileNet aesthetic. So that's the one we fine-tuned on our hotel data set. And you can see for this early convolutional layer 23, there is hardly any change. Similarly, if we go a bit deeper into the CNN layer 51, there's also just really minor changes. So actually they're almost untouched, so not a lot is happening. The deeper you go, the more complex actually the structures become that the filters learn. So if we go to the end, like almost the last convolutional layer, we can see that in the original MobileNet CNN, it's objects here almost like fish-like objects and eyes and I don't know, some sort of antelope or something like that. And you can see actually that those structures, those object-oriented structures, in a way, sort of like disappear in our aesthetic classifier, which kind of makes sense on a hotel domain because, for example, maybe eyes and fish and antelopes, they don't really play a role in hotel aesthetics. So, I mean, it's not a super amount of insight that you can gain from it, but you kind of get a bit more of a feeling of what's actually going on in this fine-tuning phase. Key learnings were that hotel-specific labeled data is key, and that through the EMD loss, we actually only needed like 1,000 hotel samples to get pretty decent results, which I believe with a regression approach would be a lot harder to get. And yeah, of course, training on GPU significantly improves training speed, so it's almost inevitable. And we will continue labeling images for the static classifier, and maybe also introduce new biases that we find desirable. For example, maybe also including technical quality. And we continuously try to improve the prediction speed. So that's why we also went for MobileNet, for example, because it's a very lightweight CNN that's quick to predict. To summarize, transfer learning, was sort of like a framework that we could use for tagging and aesthetic classification, and worked really well in our use cases. It's super important to have domain-specific data and to have clean data, garbage in, garbage out principle. And those attribution and visualization techniques, the CAM as well as the filter visualizations, they definitely helped us understand what's actually going on under the hood, and we could even improve the models, for example, by sort of labeling more pool images with rails as pools, and the classifier will suddenly learn, hey, it's not the rail that actually makes it a pool, it's something else. We open sourced basically all of the code also on GitHub. You can, it's actually, maybe it's not gonna work, so so we have, for example, this image quality assessment project here, repo. Whoa. And basically we have pre-trained models that you can access. It's all Dockerized, so it's a few lines to really use these models and predict aesthetic scores yourself in this case. There's a lot of stuff here. Also our training workflow on AWS, so there's some instruction of how you can sort of like get it going quite quickly yourself. We link to the data sets, those open source data sets. We didn't publish the hotel data. So check it out. You might find something useful there. And then, of course, we're also hiring. So if anyone is interested in working in Berlin, it's a great city. Get in touch, please. And any questions? Thank you.
So we have time for question.
Did you try different CNN architectures and didn't give a performance gain?
Yeah, we tried many. And for example, I know VGG16 quite well, and I kind of like it. And for aesthetics, I didn't get better results, but I didn't sort of optimize all the hyperparameters yet. If I would have put in effort, I'm pretty sure I could have gotten better results than with MobileNet. But the main drawback is the prediction speed, because like it has over, I don't know, 100 million parameters, and MobileNet is a lot smaller. Basically, the model file is around 30 megabyte, whereas for VGG16 is around 500 megabyte. So prediction speed was key here, and the performance gain or loss is minor in for the aesthetic service.
Exactly the same story for tagging. So we actually worked quite a lot with ResNet 50, and that guy has about 23 million something parameters. We actually even kind of floated the model in production, and then we actually realized that the kind of throughput we need is just not acceptable. So we had to go with MobileNet. This has like 3 million parameters or something. So prediction speed improved greatly, and the performance didn't actually suffer that much. So it was acceptable.
No more question?
You said that the throughput of the model during production is a key factor. Have you tried any methods such as pruning the network after training in order to reduce the number of computations during production or test time?
I haven't done that.
No, we have done no pruning, no post-processing.
How many millions images did you tag, and how you said for 2 weeks, and how many GPUs?
Basically, for we tagged 280 million images for aesthetics. We didn't use any GPUs. We used our OpenShift cluster on 100 pods, and it was just over 2 weeks, I believe. It was sort of like the setup in the end is it can do an image in 164 milliseconds, I believe, something like that. We propagate 16 images in a batch. That's kind of like the optimal size for these pods.
Okay, so thank you, Christopher. Thank you, Tanuj.